Alright everybody, here is the beginning of the review for exam number 3. This is part 1 of that exam. I'm going to do a total of 10 questions on this video, and then I'll continue on with another video tomorrow. Okay, so this first question, I know that a number of people asked me about it. This asks about chymotrypsinogen. It's identified as an inactive enzyme and is cleaved by an enzyme. Okay, so chymotrypsinogen is a zymogen, which is an inactive protease. Now that inactive protease has to be acted upon by another protease. Now through the process of chymotrypsinogen becoming chymotrypsin, one of the steps is that it stops off at pi chymotrypsin. So what we see here, however, this question is asking specifically about chymotrypsinogen. Chymotrypsinogen is cleaved by trypsin. Trypsin cleaves chymotrypsinogen, resulting in the formation of pi chymotrypsin, which then can autocleave and go on to further develop the functional enzyme. So there you go. Question number 2, when looking at the enzyme identified via the EC system, what does the second number refer to? So this EC system is kind of like, in computers it's similar to an IP address. Really it's kind of similar to an address to identify a general class and then subcategories until you actually identify the enzyme. So there's an enzyme that is 1.2.1.37, and that is one specific enzyme that catalyzes one specific reaction. The first number, the 1 in this case, is the class. The 2, however, is the subclass. So this sequence follows the class, subclass, and sub-subclass until you get to the actual enzyme itself. All right. What type of enzyme catalyzes the following reaction? Glucose 6-phosphate to glucose 6-phosphate to fructose 6-phosphate. Okay, so when you think about glucose and fructose, those are both hexoses. Those are both 6-carbon sugars. They just get rearranged. Nothing is happening in terms of removal of a phosphate group or the addition of a phosphate group. So all that we are doing is we are isomerizing our enzyme. We're not transferring a phosphate group on, we're just rearranging these carbons. Hence, we are working with an isomerase. The catalytic triad is composed of which amino acids? Now this, this sends you back to a discussion of serine proteases. So when those serine proteases are active, what are the amino acids that basically make up the active site? And there are a total of 3 enzymes, hence triad. And those, I'm sorry, not enzymes. There are, sorry about that. There are 3 amino acids that are significant for the function of this enzyme. What was kind of interesting about this is that not all of these actually participate in any sort of movement of electrons or cleaving of any bonds. In fact, one of the residues, the aspartic acid, all that it really seems to do is basically help preserve the structure of that active site. So the correct answer for this, they are B, a histidine, an aspartic acid, and a serine. Alright, so that was all with serine proteases. All serine proteases have those highly conserved residues. Okay, question number 5. What type of bond does lysozyme cleave? Well, this kind of takes you back a little bit because this is not asking directly about, well, the mechanism of lysozyme, but instead it's taking a step back and asking a more general question. So you might know everything about the mechanism of lysozyme, but it's important to know the bond that you're actually breaking. And this is a bond between subunits of sugars, and so this is known as a glycosidic bond. So we first learned about glycosidic bonds when we were talking about carbohydrates. So this does take you back quite a ways. B is the correct answer. Question number 6. There are 2 amino acids at the active site. At the active site of the lysozyme that really seem to do all the work. They are an aspartic acid and glutamic acid. Select the true statement regarding these amino acids. So it's important that you remain familiar with those 2 different residues. I talked about these kind of at great length because of the fact that whenever you see an aspartic acid and glutamic acid, your instinct might be to say, I know my instinct would be to say, oh, well, one serving as an acid, one serving as a base, but that's actually not true. So So answer option A, one residue acts as an acid and one as the base. That is incorrect. Answer option B, one residue acts as an acid and the other establishes a covalent bond with the substrate. Now that is actually the correct answer. And what we have is we start this mechanism out and we are looking at the glutamic acid as your acid, and the aspartic acid, ASP, is your, it makes your covalent bonds. So it's kind of interesting because it's not really what you would expect. Okay, now B is the correct answer, but looking at the different answer options, both act as acids, that's incorrect. D, one acts as a base and the other is involved in coordinating a zinc ion. That's kind of asking a question to reflect on your carbonic anhydrase, what zinc does in that case. Answer option E is also kind of asking that same thing. Okay, now question number 7 here asks, what coenzyme is only transiently associated with an enzyme? And so in order to answer that question, what you need to do is think back to so the correct answer for this is, it's on slide number 7, and it talks about transient or tight association with an enzyme. And the correct answer for it is a co-substrate. So a co-substrate transiently associates with an enzyme. A prosthetic group is something that is more permanent. And an example that we talked about there would be something like heme. Heme, though not an enzyme, is going to be a prosthetic group when it comes to binding hemoglobin, or within the function of hemoglobin. Okay, the enzyme carbonic anhydrase utilizes 3 histidine residues in order to coordinate which metal ion. And I just alluded to this in question number 6. The correct answer is zinc. Zn2 plus is zinc ion. So what's significant about that is that allows the change in a pKa value so that we can actually, continue and complete the function of that enzyme. So I had a lot of people ask about this question number 9. This question number 9 and question number 11. To a degree, they're they're very similar questions because they're both asking about Michaelis-Menten kinetics. Question number 9 reads, if an enzyme with a Km of 2 millimolar and a Vmax of 100 nanomolar per minute is provided with 4 millimolar of the substrate there, which of the following is true? Okay, so you can actually kind of approach this question and not even worry about those values yet. What you need to know is V sub 0 equals Vmax times your substrate concentration over your Km plus your substrate concentration. Okay, so whenever you see that, what you're basically looking at is you're looking at a ratio of your velocity to your maximum velocity. So we can rewrite this equation to read V sub 0 over Vmax equals substrate concentration over Km plus substrate concentration. Now at this point in time, it might be worthwhile to look at our answer options. Answer option A is the enzyme is performing at max velocity. B, the enzyme is performing at higher than max velocity. C, the enzyme is performing at half of max velocity. D, the enzyme is performing at below half of max velocity. And E, the enzyme is performing at above half of max velocity. Okay, so before we get into this any further, though, let's think about this. Our Km for our substrate is 2 millimolar. So if you provide your enzyme with 2 millimolar, that enzyme is going to basically be catalyzing reaction at half of the Vmax. Now in this case, we provided our enzyme with 4 millimolar of the substrate. So thinking about it in that sense, well, the substrate concentration is greater than our Km. Okay, so think about it in terms of a threshold. Have we provided enough substrate in order to perform at half of Vmax? Yes, we have. 2 is our Km. We've given it 4 millimolar. Now, when you plug all this information in, and again, you don't have to use all of it, or I don't know if I said that previously, but you don't have to use all of this information. What you do have to use is your Km and your current substrate concentration. So you could rewrite this as 4, because that's our substrate concentration, over 2, that's our Km, plus 4. So basically we are at 4 over 6. And that is our ratio of our velocity over our Vmax. Now, if you wanted to, you could go ahead and plug in the Vmax and solve for a velocity, but really this is looking at a ratio. You're at about 66% of your Vmax. So if you're at 66% of your Vmax, you're above your Vmax, or you're above half of your maximum velocity. So you can kind of work through these answer options. The enzyme is not performing at max velocity. It's not performing at higher than max velocity. Think about that. Higher than your maximum, that's not really possible. The enzyme is performing at half of max velocity. We know that that's not the case because we have more substrate. And then we're left with D and E, below half of max velocity or above half of max velocity. The answer option for that is E, above half of max velocity. Okay, question number 10. One enzyme can utilize two different substrates, A and B. If the enzyme's Km for A is 3 millimolar and the enzyme's Km for B is 5 millimolar, which of the following statements is true? Answer option A. The enzyme has a higher affinity for A. The enzyme has a higher affinity for B. The enzyme has an equal affinity for A and B. And D. The enzyme's affinity for A and B cannot be determined. Well, what this question is getting at is it's getting at the relationship between Km and affinity. And that relationship is that the lower the Km, the higher the affinity. So think about it as the enzyme wants to get a specific substrate when there is a very, very small amount present. So it's going to grab that and hold on to it very easily. So we have two Km values. A is 3 millimolar and B is 5 millimolar. So the lower the Km, the higher the affinity. We can look at answer options C and D and basically cross those out. Answer option D, the enzyme's affinity for A and B cannot be determined. Well, if you don't know this relationship, that's probably what you would arrive at, but that's incorrect. Answer option C, the enzyme has an equal affinity for A and B. If you know the relationship between Km and affinity, well then you're going to eliminate that one. And then it just comes down to, well, which one's Km is lower? The Km for A is lower than that of B, so our correct answer option is A. All right, so that's going to conclude part 1 of this video. So I hope this is helpful. I'm going to tackle the next part of this exam on my next video, which I'll be probably doing in the morning tomorrow. At any rate, I want you to do very well in this exam. And so I hope you enjoy this. Thank you.